All right, good afternoon. We're going to go ahead and start into our discussion on intermolecular forces, and this is going to sort of be our jumping point for intermolecular forces. So I want you to take your time, make sure you're taking notes as we go through this. Now, basic phases of matter and their principles that we have to look at is that gas, we say has an indefinite shape, indefinite volume, or it'll take on the shape of whatever you put it into. Liquids, of course, they'll take on the shape, but you cannot compress them. And solids, they're going to retain their shape and their volume no matter what you do with them. This is going to be sort of some of the basic of what we're going to talk about, but we want to look at how these things are going to interact with each other. So, intermolecular forces. Now, these are going to be the things that are holding, or the bonding forces that are holding solids and liquids together. Now, notice that it says intermolecular forces. Now, like you get on an interstate highway, you play on an intercollegiate team. For those who may get into sports, that means you're going to play other teams, or you're going to go on a road that goes between states. In this case, intermolecular forces means that it goes between molecules. And there are a couple of different ways that we're going to look at this. Now, intermolecular forces are weaker than ionic or covalent bonds, which are actually called intramolecular forces, or things that are inside. Example, if we look at the example that we have here, 16 kilojoules per mole to vaporize hydrochloric acid compared to 431 kilojoules per mole to break hydrochloric acid into its elements. It's very easy to break this bond that's sitting here right in the middle. It's just a hydrogen bond. And we're going to talk about, of course, hydrogen bonding. But it only takes 16 kilojoules per mole just to break that bond, whereas we'd have to put in so much more in order to break it into a hydrogen ion and a chloride ion. Now, when a substance melts or boils, the intermolecular forces are broken, not the actual intramolecular. And again, we're trying to get the difference between these out, and I hope that you'll be able to catch it. If there are any questions, again, write them down so we'll be able to address them in class. Now, the boiling point is going to reflect the intermolecular force strength. What do I mean? That means if there's a high boiling point, that means that those forces are very attractive, they're very strong. Whereas if there's a low boiling point, there's going to be a low attraction. A high melting point reflects, again, strong attractive forces, meaning they're holding on to each other in order to forming bonds and linkages between each other. Now, four main types that we'll deal with. First is an ion-dipole force. 2 is a dipole-dipole, London dispersion forces, and hydrogen bonding. Now, the London dispersion forces is the other ones that we talked about, the van der Waals forces. So, whenever you see London dispersion, think van der Waals. But also that means on your test, make sure when you're thinking van der Waals, make sure to write London dispersion forces, or LDF, which I believe both will be accepted. Now, hydrogen bonding, of course, is going to be a special type of dipole force, and it's not going to be what most people think, where it's inside of the bond, but it's actually the attraction to another molecule, again, making sure that that is very clear. Now, first one we deal with is ion-dipole forces. We have an ion in solution with a dipole. Remember, we said a dipole is a molecule that has two different poles, has a positive and negative end. Because of that, they'll be attracted, of course, to an ion, which is a charged particle. Now, this will be the strongest of all intermolecular forces. Just because of that difference in charge, it makes a huge difference in the ability to pull. Give an example. Once sodium chloride is dissolved in water, you end up with our sodium and chloride ions floating around. Once they're broken up, they're going to attract molecules of the opposite charge, or parts of the poles of molecules with opposite charges. The next part that comes in is our dipole-dipole. This is existing between two polar molecules, the negative end of one with the positive end of the other. And this, of course, we saw was measured in many times the number of Debye's. This is going to be weaker than ion dipole forces, but for what we're talking about, this is actually going to be sort of in the middle of the pack. Two molecules have about the same mass and size, then the dipole-dipole forces will increase with the polarity increasing. So as long as they're about the same size, as the polarity increases, also that bond or that strength between them will also increase. Given a couple of examples, taking a look at propane given to you at the beginning, and compare the molecular weight with the dipole moment, as well as the boiling point. You notice that the higher the value, looking at acetaldehyde, you have a 2.7 dipole moment, or 2.7 Debye's, and you also have a very high boiling point at 294 degrees Kelvin, whereas acetonitrile, CH3CN, has molecular weight again, 41, but you also have a very, very strong dipole moment. This is a very, very polar molecule versus at the beginning where you're dealing with propane, which we've dealt with before, is just basically a non-polar molecule that we're going to end up dealing with because of how things are arranged around it. Looking at the dipole moment and also the boiling point that's given with it, the lower the attractive forces, the lower the boiling point will be. Now, not London dispersion forces, or van der Waals forces. These are going to actually happen between nonpolar molecules. Now, these will also be the weakest of bonds that we're going to have to deal with. Why? Because it's all as a result of the movement of electrons. We'll have a little video clip in class that will help us understand this. Now, one molecule's electron cloud can become distorted, causing instantaneous dipole. What it's saying is, if I have electrons that are moving around, based on how they move, it's going to change the pole. Because there's no set pattern that they must follow, there are some times where we'll have electrons that end up on one side of the molecule for just a few moments, a few seconds, and in that time they create a slight negative and a slight positive charge. Now, this is of course constantly changing because the electron's movement is constant and random. The forces between instantaneous dipoles, of course, London dispersion forces, which I believe it is again okay to abbreviate LDF on the actual exam, and we'll go through some examples like this. This is giving you an idea of what's actually happening, giving the example with helium. You have two helium atoms, and because of the movements of electrons, you notice here on this side that while helium atom 1 has a balanced approach, helium atom 2, the electrons have moved from one side to the other. This is going to create a slightly negative charge on that side, which is also going to pull a little bit on the nucleus of the first helium atom. This is what we mean by instantaneous dipole. It happens very sporadically, and it happens and just changes how things will look. But all in all, in this, the more of these that we have, because it's a difference, because it's that 0.1 or that very small difference, the stronger it'll be. But on its own, a single London dispersion force will be very small, very weak. The larger the molecule, the greater number of electrons, which means it's easier to actually create the instantaneous dipole. And we looked at an example of this in class. So, looking at this, the boiling points for halogens and noble gases, which is where we'll usually find this. The larger the molecule, the more electrons. You see the increase in the boiling point, and that is again all due to LDF, or London dispersion forces. It also is going to depend on the shape of the molecule. the greater surface area, the greater the dispersion forces. Give an example of what we have here. We have pentane, two different examples of pentane, as well as neopentane. The more areas where it can actually form these bonds, the better. And so if we look at our example here, we can have bonds that form between each of these hydrogens here. That's going to set us up to have actually more London dispersion forces and be able to have a stronger bond. One of the examples that's good to note is, even though it's a nonpolar molecule, is when we look at paraffin wax. If you put it in water, it doesn't dissolve. Why? It's a nonpolar molecule, and it's joined and held together by London dispersion forces. But there are so many of them that it doesn't get broken down by the water. Now, hydrogen bonding, which is our last of the four that we talk about, is basically a special case of dipole-dipole forces. What do I mean? When we look at the boiling points of different compounds, hydrogen fluoric acid, of the hydrogen-oxygen bond, as well as nitrogen-hydrogen bond, we look at them being as abnormally high, and that's because the hydrogen bonding force is so strong. Hydrogen bonding requires, first off, a hydrogen has to be there, but it's going to be attached to a highly electronegative element. Most of the time it's going to be fluorine, oxygen, or nitrogen. Because of that difference, and because of hydrogen not having that ability to shield its nucleus, we're going to end up with a definite positive and negative end to the molecule, or to the bond. Now, it also needs an unshared electron pair from a nearby small or highly electronegative atom. Again, usually fluorine, oxygen, and nitrogen on another molecule. This is going to allow it to have a definite attraction between these two. As we continue to look at these examples given to us, we notice that between our water molecule, we'll end up with a stronger bond here, or here, and here. This is going to allow us the opportunity to actually have hydrogen bonding to take place. Now, these bonds are actually going to be one of the stronger that we deal with in terms of our intermolecular forces. Hydrogen bonding will be the technical highest outside of ion dipole, which we don't really utilize too often. Down here at the bottom, we notice we have our nonpolar molecules, looking at the temperature and their boiling points, whereas as we look up on the scale, these are dealing with our polar molecules, which water, of course, being the highest. Looking at our Celsius scale, of course, there are some that go above that, but looking at the boiling points of these solutions. This is going to bring us to the end of section 1. Go ahead and take your notes on this, reading along with the section. If it seems a little jumbled, write down any questions that you may have and we can discuss them in class. Have a great afternoon, and I'll see you in class.